If you knock on a window pane, your senses tell you it's a standard, rigid solid. But strictly speaking, it isn't. You are actually looking at an amorphous substance. A true solid relies on a rigid, highly organized crystalline atomic lattice. An amorphous substance has a homogeneous texture, meaning its internal atomic structure is a fluid, randomized mess that got frozen in place before it could organize itself. Getting a material to reach that frozen state requires intense heat. The primary raw ingredient for the vast majority of commercial glass is pure silica, which is essentially refined sand. To melt that silica down into a workable, glowing liquid, you have to subject it to massive thermal energy, often exceeding 1700 degrees Celsius. But melting pure silica is only half the battle. If you cool pure molten silica, the resulting material is completely impractical for commercial use. It is intensely brittle and far too hard to physically manipulate into specific shapes without shattering. Making glass functional means treating the furnace like a highly technical chemistry lab. Engineers have to mix specific additives into that raw sand to strip away its brittle nature and manually build in the exact physical traits they want. This table outlines the recipe for common glass. Silica serves as the major constituent. Engineers add lime, making the hot glass highly fluid so it can be physically drawn or blown. Next, they drop in soda, an accelerator that injects physical durability. Once that baseline is established, the chemistry gets highly specialized. If a manufacturer adds potash to the mix, it alters the material's basic thermal physics. The glass becomes infusible and highly fire-resistant. If the goal is high-end aesthetics, they introduce lead oxide. This specific chemical compound drastically increases the density and weight of the material, while giving it a brilliant, reflective shine and noticeable color clarity. Before a single tool ever touches the molten material, its absolute physical limits, how hot it can get, how hard it can be struck, how it catches the light, are completely dictated by these base chemical modifiers. The same strict chemistry applies to color. You don't dye molten glass, you force a chemical reaction by mixing in reactive metallic pigments. This reference chart details those specific metallic pairings. Introducing cobalt oxide yields a deep blue, while adding gold chloride chemically shifts the material into a vivid ruby red. With the chemical recipe locked in, the molten liquid moves to the forge. It must be aggressively forced into its final shape before cooling. For commercial hollow vessels like bottles and jars, the process relies on blowing. By trapping air inside a glob of molten material on a rod, workers expand the interior, thinning out the walls until it reaches the exact volume needed. For continuous flat shapes like building windows or structural rods, manufacturers rely on drawing and rolling. They feed the viscous liquid through heavy industrial rollers, stretching and flattening it into endless uniform sheets. The specialized tool you eventually hold in your hand is the direct result of these two distinct phases, a highly calculated chemical recipe followed by a violent physical forming process. Glass is a highly customizable blank canvas. Engineers dial in the exact structural properties they need to match the environment the material will face. When specifying glass for commercial and industrial use, the selection process is dictated entirely by extreme environmental demands. Take the chemistry lab. If you are flash boiling chemicals, standard window glass will shatter instantly from the sudden temperature change. Lab environments require Pyrex or borosilicate glass, which are specifically engineered for high thermal shock resistance and extreme chemical durability. If you need to manipulate light for specialized photography or industrial sensors, you require optical glass. By mixing in phosphorus and cerium oxide, the material is engineered to specifically absorb incoming UV rays while refracting visible light perfectly. Then there are environments built around extreme physical security, like jewelry store displays or high-volume bank teller windows. In those scenarios, chemical hardness alone isn't enough to stop a projectile. They deploy bulletproof or laminated glass. This is manufactured by placing flexible vinyl plastic between alternating layers of glass, then tightly pressing them together. When struck, the outer glass breaks, but the inner plastic stretches to safely absorb the kinetic impact. From a beaker holding boiling acid to a skyscraper window resisting gale force winds, none of it is a natural occurrence. Every piece is the calculated outcome of a deliberate, invisible chain of chemical decisions and mechanical engineering.